Hi, this is Professor Pradyot from Leadib Academy. We are discussing IBDP Chemistry SL Paper 2, November 2019. So we are going to discuss the video solutions, but more interestingly, we'll be understanding the underlying concepts, behind these solutions so that there would be a deeper clarity. If you are interested in having much detailed kind of understanding of these concepts, you can visit our website, that is www.leadibacademy.com, where we are uploaded all our courses for chemistry, physics, maths. You will find them very interesting. Okay, so let's begin. We are looking at the question number 4A1. So what it says that there is a citric acid molecule, okay, and we need to identify a conjugate acid-base pair. Okay, so how to do this? Okay, so simple. Okay, so what we can do, this is an acid, this is a salicylic acid, so obviously this is the base. Okay, water is acting like a base, and we know, if you observe very carefully, if we subtract, okay, if we take out proton, okay, this is like a proton, if we take out, what we get is its conjugate base. This is the conjugate base, okay, of this citric acid. This is the citrate ion, citrate. Okay, and now if we talk about this, if we can observe that if we add proton, because it's a proton acceptor, this base as per the Bronsted and Lewis theory, okay, Bronsted and Lowry theory, B and L, okay. So this is the base, so obviously this has to be conjugate acid. Very, very simple. This is as per Bronsted and Lowry, okay, theory. So what we can learn, acid minus H plus is equal to conjugate base, and base plus H plus is equal to conjugate acid. Extremely simple concept. Okay, so you can easily this one. So if we have to define, we can define any pair, okay, out of this. Both are correct. Hope this is quite clear. Okay, let's look into the question number 4A2. The value of the equilibrium constant for the first dissociation at 298 Kelvin is so and so. So what we have been given is the dissociation constant. If you recollect, dissociation constant of an acid, okay, it is given as 5.01 into 10 raised to minus 4. Means very, very, very small. Okay, this is very small. So what does it indicate? Dissociation constant indicates that if it is small, this implies that this acid, okay, dissociation is going to be partial or very small dissociation. Partial or weakly dissociated. And therefore, we can term this citric acid as a weak acid. Okay, because stronger the dissociation, that means finally, please remember that everything depends on this. These are the hydronium ions. Okay, so higher the number, okay, higher the dissociation, that means we are going to get this H3O plus, because finally H3O plus or H plus, they are basically determining whether the acid is strong or weak. Okay, so if dissociation is less, it means that this acid is not dissociating completely. That means we can think of that equilibrium is lying on the left hand side. Okay, so we can interpret in any manner. Simple. And we can look into the value, okay, which is very, very small. That means it is hardly getting dissociated. So by any this one, the conclusion is that this is a weak acid because there is not going to be much dissociation. Okay, there is a partial or weakly dissociation. Okay, very, very straightforward. Okay, question number 483. The dissociation constant of citric acid, okay, the dissociation of citric acid is an endothermic process. State the effect of hydrogen ion concentration H plus on the equilibrium constant, okay, and on the equilibrium constant of increasing the temperature. So let me put this reaction. Okay. So this is the reaction and this is the endothermic. Okay. Endothermic means we need to supply the heat. Okay. Endothermic, that means the change in the enthalpy is greater than 0. It is a positive one. So whenever we increase the temperature, we know that the forward reaction will be favored. Okay, because it is an endothermic reaction, so the forward reaction, will be favorable. It means that there would be more production of H3O plus, means H plus. Okay, because please remember H3O plus and H plus, they are same. H3O plus is identical to H plus. So obviously, if forward reaction is favorable, that means there is going to be more release of H3O plus, means H plus. Okay, so definitely the concentration of hydrogen ion is going to increase straightforward by increase because of the endothermic. Okay, because it's an endothermic and we are increasing the temperature, so it is favorable. Now let's look into what is equilibrium constant. We know very well that equilibrium constant is the function of temperature. It means higher the temperature, higher the Kc. Okay, simple, straightforward. As a matter of fact, the Kc can be varied, equilibrium constant can be changed only by changing the temperature. So if we are increasing the temperature, the Kc is going to increase. So increase. Okay, so this also is going to increase. Simple, straightforward. Okay, very, very simple. If it would have been exothermic, the effects would have been exactly reversed. Okay, simple. Okay, let's check the question for B. Outline one lab method of distinguishing between solution of citric acid and HCl of equal concentration, stating the expected observations. Okay, so first, let's look into this citric acid and HCl. We know very well HCl is a strong acid. So what does it mean? We know very well by definition it is going to get dissociated completely and it is going to release more of a H plus. While citric acid, we have seen from the above reaction, that it is basically a reversible, and if we have seen its dissociation constant also very less. So this will be in the smaller quantity, okay, concentration of this, and this is in the higher concentration. So what would be this one? Straightforward. So with this, we can clearly say that means lower the H plus, that means high pH. Okay, and in this case, low pH. So we can compare their pH and the one, okay. So HCl will have a lower pH. So this is a straightforward test which we can look into. Okay. Another way, looking into the same concept, applying the same, higher the concentration, okay. So we can say another point, okay. So this is the one point. Then second point could be due to higher dissociation of HCl, its conductivity will be high. Okay, simple. It will be much higher as compared to citric acid. Why? Because it is finally the conductivity is nothing but how many ions are present, okay, in the dissociation. Then the third one, that we take metal carbonate, okay, MCX3Y, and if we add any acid, there will be evolution of CO2. So if this evolution of carbon dioxide is very high, then we can straightway say that means that is a strong acid. So high evolution with the high strength, that means it's a strong acid. And a weak acid will not evolve so much of CO2. Okay. So these are some of the techniques, okay, what we can use to differentiate. Okay. Extremely simple logic. Hope this is quite clear.